Hi everyone, my name is Kayvan Karami from Glasgow University. My topic is about heavily doped gun cap layer on aluminum nitride gun Mustang. The outline for today's talk is why I've chosen aluminum nitride gun hand with heavily doped gun cap layer. Then I'll talk about annealed and non-annealed homing context and the structure. Then I will talk about aluminum gun Mustang structure. Then I will go through the fabrication process, followed by measurements and results, and at the end, the conclusions. So I have chosen aluminum gun hand with heavily doped gun cap layer. The final goal for my project is to build high-power devices in higher frequencies, especially in W band. To do so, aluminum gallium nitride is a good gallium nitride hand is good candidate because of the having a larger band gap compared to standard argon gun hems, which that increases the charge density up to 3 times as much as the standard argon gun hems, which that helps having higher power in higher frequencies. Also, the benefit of using aluminum nitride gun hems, they have very high aspect ratio of LG over D, which is due to the thin barrier layer of 3 nanometer, which that helps downscaling the device in order to operate in higher frequencies without causing short channel effect. Also, heavily doped gun cap layer would help to reduce the homing contact resistances. Here is the ctlm structure that I have used to measure the homing contacts. On the right is the measurements, which is the one with the red squares are the non-annealed measurements, and the one with the blue rectangles are the annealed measurements. The non-annealed measurements were between 5 to 10 ohms millimeter, which they were high to be used at the device level. But after annealing at 800 degree in two environment for 30 seconds, that that resistance reduces to 0.4 to 0.6 ohms millimeter. Here is the argon gun Mustang device structure. On the top, figure A is the wraparound device, which is used for this test. And figure B is the device structure. From what you can see is here's the 5 nanometer heavily doped gun cap layer, followed by the aluminum nitride vanilla of 3 nanometer. Then the gallium nitride channel layer of 1.4 microns and gallium buffer layer of 0.8 microns, followed by aluminum nucleation layer and sapphire substrate. And this is the silicon dioxide deposition, which has been etched and deposited the silicon dioxide for 5 nanometer of silicon dioxide. Then followed by depositing the gate metals. Gate size is 2 microns with the gate to source spacing of 3 microns and gate to drain spacing of 5 microns. Here is the fabrication process. So I started with depositing homing contacts along with the markers with titanium, aluminum, nickel, gold, 20, 180, 40, 180, 100 nanometer or metal stack, followed by lift-up process. Then I anneal them at 800 degrees for 30 seconds. After that, I've removed the heavily doped cap layer under the gate region using SF6O2 gases using RIE 80+. Follow that, I deposited the silicon dioxide gate dielectric, and then I deposit the gate metal stacks using nickel gold 2400 nanometer metal stack. Figure A is the AFM step size, which is which clearly shows the 5 nanometer has been etched. This is the etch area, and this is unetched. So you can see the 5 nanometer is etched fully. And the figure B is the AFM image again, which is shows the roughness of the image before and after, which the roughness is quite similar, very similar. It was 2.1 nanometer before and 2.18 was after the etched. And on the bottom, this is the SEM image of the fabricated device. You can see this is the drain, and this is the gate. This is the edge area under the gate and the side of the gate, and these are the unedged area, the cap layers. This is the measurements and results. So this is the IV curve, which is biased at VGS from -9 to 3 volt, with the highest of 3 volt, which we get over 800 milliamp per millimeter of drain current. And on the right hand side, this is the transfer characteristics, which shows the transconductance of over 130 millisiemens per millimeter, and a threshold voltage of minus 6.8 volts. Here are the leakage current measurements and breakdown voltage. On the left, the gate leakage current shown to be 10 to the power -5 milliamp per millimeter, which is the results quite high, but that could be improved using the high K dielectrics such as aluminium dioxide or hafnium. On the right hand side, this is the breakdown voltage of 73 volt at off state of VGS equal by 10 -10. This is the conclusion. Now we have achieved low ohmic contacts of 0.4 to 0.6 ohms millimeter. We have selectively etched the heavily doped cap layer under the gate regions, and we achieved the high drain current density of over 800 milliamp millimeter in a threshold with a threshold voltage of -6.8. Maximum transconductance of over 130 millisiemens per millimeter. And again, the high leakage current could be improved using high K dielectrics, and breakdown voltage of 73 volt is achieved. Thank you everyone for listening.